This is it, right? Kind of a crane operator. So there's a row. Do you know why this is row? This entire length from the pole to your block, wherever that thing lies, is a row. Why row? It's a Greek letter, but why row? Row is equivalent of our which letter?
R.
R. I know, radius, you get it? But then they didn't want to say R because R is already taken. R is this length right there, isn't it? You know what I'm saying? R is our polar coordinate R, so it's still same R, theta. So see, whatever this thing is, it's gonna cast a shadow down here, right? So distance from the pole to that side is called R, you get it? And this is theta. And there's another angle, which is phi, which comes down from the vertical z-axis. So this is the line where phi is equal to 0 to pi over 2 and then goes down to pi. We rarely go beyond pi because instead of going that way, we actually rotate this crane around. So we adjust it with the theta. Okay, so y'all with me, which is which? Do you want me to find the conversion between Cartesian to spherical one more time, or do you remember? You don't. Okay, let's do this. Okay, I'm gonna shut this thing down and throw another picture, okay? Similar picture. So before we have any volume, okay, say we have that kind of angle. So I'm gonna draw the same style axis here. So let's say this is z-axis. Something like that. Similar, right? Yeah, about like that, a little bit more that way. Okay. So suppose there is a point hovering somewhere up there, okay? So that point that is hovering, we can reach it from this pole to somewhere, let's say up there. Okay, that's our like vector, if you will, that points towards this coordinate. And that coordinate is x, y, z. So far so good? So let's just draw what x, y, z means. If I drop this thing down, I'm gonna do that with red. I'll just do it with this. Say you come down to this point, is the shadow of this point up there. You get it? And then we reach that point from here. So far so good? Let's just think about that triangle. So this is a right triangle. So far so good? So do you see that this much is z at the moment? You don't see that? Okay, let me draw the rest of the dotted line. So do you see this is x and this is y? I'm going to put it on the other side. And that's z. Are we good? So we have x, y, z. You get it? Okay, now, and this length right there is called rho, Greek r. And we are calling this thingy r. Good. Actually, I'm going to put this into blue letter. Okay, I'm going to put that in red. Ah, red. So all the spherical is in red, and then all the Cartesian is in blue. Okay, and this angle right there is called phi, and this angle right there is our usual theta. So on xy plane, we have regular polar coordinate going on, r theta. Good. And then we raise this. So do you remember cylindrical coordinate at least? That was r theta, and then this was z. You know what I'm saying? So z is still the same, and then instead of xy, we switch r and theta. So let's get that much out of the way, shall we? Okay, so do you remember this x? This is a right triangle too. So our x was r cosine theta, and your y was r sine theta, wasn't it? Do you want me to go back and revisit that, or are we good this much? This is this r times cosine, and this y, this is the y, is r times sine theta. Get it? Get it? Okay. Now, concentrate on this triangle. This is a right triangle. So this side, well, this side first. R is equal to, do you see now that R is equal to rho sine phi? Do you see that? R over rho happens to be sine. You want me to draw that thingy? Okay, maybe I should draw this. So at least you see this is phi, right? Parallel lines, alternate interior angle. Eh? Say something. Are you getting this or not getting it? I need to know. Okay. Alrighty. And was z here, wrong color. Z is equal to rho cosine phi. Good. This side is cosine because that's your phi. Say yes. Okay, now I'm going to make a substitution. I'm going to move this thing over, switch the places. Okay, let's put it right there. Now, let's go. So this R happens to be rho sine phi, substituted right there. So your x is rho sine phi cosine theta, isn't it? Good. Okay. Well, what about this? Well, once again, R is rho sine phi, and then we have sine theta now. Good. And this thing stays the same. So your z is still rho cosine phi. Bang. So this is the conversion. So if you have spherical coordinate, rho phi theta, instead of 3 lengths, you have 1 length and then 2 angles. Get it? So this is like 3D version of polar coordinate called the spherical coordinate. And then this is how you go there. Then how do you go the other way then, right? The other way is super Pythagorean theorem. So rho squared, of course, is x squared plus y squared plus z squared now, isn't it? That's one way. So if you have x, y, z, you can calculate rho. And then r squared is, of course, x squared plus y squared, those two, right? And having that, then you have this convenient relationship. Actually, I'm going to trade a place. I'm going to have it like that. So regular tangent theta was y over x, eh? That's how we figure out theta. And then there's a relationship here, and that is tangent phi. Let's just look at what tangent phi is. In this triangle again, tangent is this hypotenuse over adjacent, isn't it? So that is r over z. And of course, r is this r right there, right? So once you compute r, you can calculate phi. So these are the transformation from Cartesian to spherical and spherical back to Cartesian. Good. Okay, having said that, now we have to figure out what dV looks like. And that takes us to this picture now. So one of this triangle is what I drew here, right? But let's vary these things a little bit. If you vary rho tiny bit, so create d rho. Do you see that's this d rho? If you vary phi a little bit, then it's going to create little arc, right? That happens to be this arc right here. Good. But arc length formula is radius times the angle. So this is rho d phi now, not just d phi. D phi is this much right here. So that's rho d phi. Good. Now the most difficult part is if you vary theta a little bit, then it's going to create that arc, right? That arc will be same as this thing up here. Good. So since this is a shadow, so that arc length right there is same arc length as this, isn't it? Can you see me? This pointer in my hand, it's like with my finger, is moving like this. So this is, of course, r d theta, right? R times d theta. But then our r up here happens to be rho sine phi. So this becomes rho sine phi d theta. Good. Now let's put it together. So dV in this volume of this little tiny box is d rho, this thingy, times this thingy, which is rho d phi, times this thingy, which is rho sine phi d theta. This sine phi comes from this side. So sine phi is here, that goes with d theta. Are you confused yet? You got this? So we have, here's rho, so rho square, sine phi d rho d phi d theta is our dV in spherical coordinate. How about that? We kind of did this before when we did moment of inertia. Do you remember forgetting moment of inertia? Yeah, okay. Well then, having said that, can we calculate this volume? Okay, so let's just get this thing. Volume is below this sphere, so this is part of the sphere. Do you see this is sitting on the pole right here? This is not the sphere centered at the origin? Right, okay, because there's a C, bring it over, and then center is at half, right? And then above the cone, this is the cone. So that kind of looking, what do you call it, icy, that when you go to Disneyland and you buy this, the shaved ice cone thingy that you buy. Can we calculate that volume? Okay, let's do it. So our dV is from above rho square and sine phi, and then d rho, d phi, and d theta. Okay, this was an easy one. Okay, so first look at. So your volume will be triple integral of, now here's the difficult part, from where to where? Right? Okay, let's do it methodically, inside one out. So rho varies from here to that surface, correct? What is that surface in spherical coordinate? Oh my God, look at this. Remember this? Right, so what is this thing? Or you can feel it. Do you see that thing is rho squared? What is z? Was it rho cosine phi? Well, that means either rho is equal to 0 or rho is equal to cosine phi, right? But rho is equal to 0 is a point, so that's not what we want. So do you see it's this one? Okay, wow, can you actually feel it? If you think, go back to polar coordinate, and then, cosine was the circle now, wasn't it? Yeah, kind of like that. You get it? But this is zx, it's not SR. You know what I'm saying? Okay. Can we feel this cone? Do you feel that this is phi is equal to pi over 4, or do you want me to analyze it? How many of you want to see this analytically? Or can you feel it? Okay, who the hell am I kidding? Okay, I'm gonna do it here. Z is equal to square root of x squared plus y squared. Messy handwriting. X squared plus y squared, right? Then do you at least see this is r squared? So z is equal to r. So far so good? That means 1 is equal to r over za. Right? And then we take inverse tangent on both sides. You know what I'm saying? So what's the inverse tangent of 1? Right? Right? What is tangent of r over z earlier? Oh, there we go, right? That's phi. You know what I'm saying? So what we have is, this is phi. So that tells you pi over 4 is equal to phi. But isn't it better to just feel it, that angle coming down, pi over 4? You know what I'm saying? So that's phi is equal to pi over 4. Ooh, see, feeling it is infinitely better than analyzing it. Now it's downhill now. So let's set up the limit. So rho will vary from 0 to cosine phi. Good. And phi will vary from 0 to pi over 4. Good. And theta will vary from 0 to 2 pi. How about that? No sweat, huh? And then we have rho square sine phi. Did I write the r there? I meant the rho. I wrote r here as well. D rho, d phi, d theta. Good. Okay, then it's really downhill from here. So 0 to 2 pi and 0 to pi over 4. And this is rho cube over 3 from, and then sine phi from 0 to cosine phi a. Say yes. Okay, and then d phi and d theta. And now plugging this thing in, so 2 pi over 4, so we have 1/3 cosine cubed phi and sine phi, and then d phi, d theta, hey? Do you see this is a u sub? This is u and that's your du, eh? And could we do this in our head? Okay, so we have 0 to 2 pi, and then we'll have 1/3. Good. And this is just u du. All we need is a negative sign, eh? And then cosine to the force phi, therefore 1/4 from 0 to pi over 4. How about that? Good? With me? So we use this. Do you see we don't have data in here? So can we just evaluate data and just pick up 2 pi? So we'll have 2 pi times 1/12. And then we have this minus that, right? So we have, I taken out 1/4 out here. So 1 minus, what's cosine pi over 4? 1/2, and you take force power, right? Right? So we have 1/4. You with me? So we have pi over 8. So A, we have to find the centroid, meaning center of mass of this hemisphere, right? Okay, I mean, orientation doesn't matter, but I decided to put it like this. Okay, now from the symmetry, and this is the homogeneous hemisphere, meaning density is constant, right? No density function. Good? Okay, now, then let's just figure out the density, and I don't want to use rho because I'm going spherical coordinate. That is the mass of this thing divided by, what is the volume of a sphere? Would that be 4/3 pi r squared? So in this case, half of it, so 2/3 pi a cubed. Good. So what we have here is 3m over 2 pi a cubed is the uniform density of this hemisphere. You with me? Okay, then let's start. And we know the mass of this thing is just m now. We don't have to integrate to find the mass. So all we have to do is calculate the z-wise. Let's call it, what did we call it? Is it m sub z, was it? I forgot the letter. Whatever. And then we have to put the density here, and then we put z here, and then dv all over this region E. Correct? Okay, that is equal to, and then of course we are going to go to spherical coordinate, correct? So we have D. What is Z in spherical coordinates? Somebody tell me while I figure this thing out. From 0 to, we'll say A. This is radius of A. And then phi will vary from 0 to pi over 2 hemisphere, and theta will vary 0 to 2 pi. Did anybody figure out what C is? Oh, come on, people.
Rho cosine phi.
Rho cosine phi. Okay, and then what's dv then?
D. Okay. Sorry.
Yeah, there's a
it would be d theta, d phi, and then
there's a sine phi.
d rho.
And then d rho, d phi, and d theta. How about that? Yeah, I see, getting rusty, aren't we? Okay, let me simplify that. 0 to 2 pi, 0 to pi over 2, and 0 to a of d rho, d rho cubed, and then sine phi cosine phi, right? I really don't like to integrate sine p cosine p. I guess we can do it. Chain rule. Do you want to do that? I mean, with the u sub, or do you want to convert with the identity and 1/2 sine 2 phi? Of course, 1/2 sine 2 phi is infinitely better, isn't it? And then d rho, d phi, d theta. Y'all still with me? Okay, let's integrate. So 0 to 2 pi and 0 to pi over 2. And then we have, should we take these constant outside? Let's not yet. So we have d rho, not rho. We'll have rho to the 4th power, right? So we have 1/8 now. So far so good. And then from 0 to a, sine 2 phi, d phi, d theta. Y'all with me? Say yes. Okay, now that becomes a. So far the constant is a to the 4th power over 8. Good. And then 0 to 2 pi. Oh, we had d. D is constant. Let's put d. Dang it. I'm going to put it in front right there. Good. And then we have, this thing is cosine 2 phi, so we pick up another 1/2 here. Good. Say yes. Okay then, start evaluating, taking that half, well, yeah, taking that half out. So we have d a to the 4th power over 8, we're 16 now. Good. And then cosine, if you plug in pi over 2, that's cosine of -1, right? I mean, that's -1, and plug in 0, that's 1. Wait a minute, we get a negative, did I? Oh, there's a negative here, right? Okay, I forgot about that negative sign. So this thing gives me 2. So I shouldn't have taken that 16 out, so change that back to 8. That gives me 2. So if I just keep that 1/2 in, that whole thing gives me 1. Good. Say yes. And then I have theta from 0 to 2 pi. That will give me 2 pi now. So what I have is pi d a to the 4th power over 4. So far so good. Say yes. Now, then, my center of mass in z direction is that thingy, pi d a to the 4th power over 4 divided by the mass. You know what I'm saying? Okay. Well, d. Can somebody substitute that d expression in for me? Okay, I'll do it. So m's cancel, so I have 3 over 2 over 4, so I'm gonna have 3 over 8, right? And I will have pi's cancel. A square is there. And everything else cancels, right? How's that? Did I get that right?
Wouldn't it just be 3/8 A?
3/8 A, oh yeah, 3/8 A. Which makes sense because this has to be purely geometrical, should not depend on mass, right? So 3/8 way of the somewhere here. Let's say it's there. You know what I'm saying? So your center of mass coordinate is 0, 0, 3/8 of A. You get it? Okay, that's A. Let's do B. So part B is we have to find the moment of inertia. But we are not rotating it the way we see. We have to stand it up and rotate because about the diameter of the space is what it says, right? So I have to redraw the picture now. Good. Okay, let's redraw it. Which will be a little bit of headache, but hey, it's okay. Say we have that. Okay, and then say it looks like that. Okay, now we have to put the axis correctly. Now we have to be very careful. The way I did it in the Dropbox note, let me try to make sense of it. I put the z-axis here, and that was obvious. And it's what you're wondering is why the hell did I put the x-axis into that negative direction? Did you wonder about that? This is my x, and this is c. And then my y-axis, I had it stick out to this side, like that. Why? Because of my limits of an integration of my data. I want my data to vary from 0 to pi like that. You know what I'm saying? Forget it. In hindsight, I regret that. What I could have done was this. Oh, now my hands are... I should have probably done this, right? Yeah, this is infinitely better picture. Like, why did I do that? Okay, let me redraw it. Let me put the x-axis back here. Let me put x in the usual traditional way, and then y out here. And then it's a little unclear which is, this is the front. This is A right here. You get it? And this is A. That's A. Better? Yeah, this is so much better picture. Okay, now what we have to do is moment of inertia is mr squared, correct? Right. So my d, let's start right there. My di is equal to m dm and then r squared. Good. Then what is my dm? Well, this is my dv, isn't it? So this will be same as r squared and dv. We are going spherical again, right? dv is, I'm going to leave space, I'm going to erase this, rho squared sine phi d rho dv and d theta, correct? What is r in spherical coordinate then? Say this, there's a little particle right here, and it's going to rotate. This is r, you know what I'm saying? And there's that particle right there. So it's our usual r. Do you remember that r is equal to rho sine phi? You don't remember? R is equal to rho sine phi. That's where this sine phi comes from, rho sine phi. You want me to draw the picture for you again? Ne, you got that? Okay, so this is rho, getting a little more space, that's a little cramped up. Put it out there, rho sine phi quantity square. That's my DI. Good? Okay, now, then your moment of inertia, I is spherical coordinate. Data varies from here and on, right? So 0 to pi now, and then phi will vary from 0 to pi, and rho will vary from 0 to a. So far so good with the limits of integration? So far so good? Okay, I forgot one little thing. Can you see what I forgot here? I forgot density, right? dm, this is dv. So I have to put in density back. Get a little more space there, and then I have to put density right here. Good. dm is d, density times dv. Alrighty, so I'll have d, and then rho cubed, and sine cubed, and d rho, d phi, and d theta. How about that? Y'all with me?
Would it be rho to the 4th power?
Oh, the 4th power. Nice catch. Now with me? Okay, let's integrate. So I'm gonna take the d outside here. 0 to pi, 0 to pi, and this will be rho to the 5th power, therefore 1/5, and 0 to a, and sine q phi, d theta. Good. So a here will give you d a to the 5th power over 5 outside. Now this sine q phi, should we recycle our work from that your project, or you want me to evaluate it for you? Here is sine q phi. What do you say? It happens to be 4/3, but I can evaluate it while I'm here. Nay, just use it. Who wants to see it? Okay, we'll just use it. Then that's sine q phi, so we only have, I'll just write down 4/3. And then we'll have 0 to pi, be careful, theta, d theta. And this thing just gives you pi, right? So what we have in total is we have 4 pi d a to the 5th power over 15. And that's it for now, right? Okay, now we have to plug in density back. So if we plug in density back, wow, it's too much algebra. It'll turn out to be this. I just totally did that in my head.